Good afternoon. Just picking up with what we have been working with concerning radical and absolute value equations and looking at the set of problems from section R5. Okay, and we have working with, again, radical equations. And we have for the case in number 103. Okay, so we're looking at radical equation where we are looking at trying to solve for x. And for this equation, we have that 1 is equal to negative 2 plus the square root of 2x plus 7. Okay, so for what we have here, the radical term is on the right, and I can isolate this upon adding 2 to both sides. Okay, so for what we have in this equation, okay, so I'm going to isolate the radical. And the radical term is the only place where we have x to exist. Okay, so adding 2 to both sides. Okay, so we have 1 plus 2 is 3. And we have that 3 is equal to the square root of 2x plus 7. And again, we have an even root radical. And again, with the square root that we have with the square root of 2x plus 7, so we have an even root, and with even roots, again, we have with the principal square root rule. Okay, an even root expression, including like a square root expression, cannot reduce to a negative constant. Okay, so we have a positive 3, and so we can proceed and looking at the follow through. So I can eliminate the presence of the square root upon squaring both sides. So for what we have here, okay, we have 3 squared is 9, and the square root of 2x plus 7 to the second. Okay, again, the square eliminates the square root. Okay, so we have that 9 is equal to 2x plus 7, and we have with this two-step linear equation. Okay, so we can isolate the x term, and so for what we have in this case, all right, so looking at deducting 7 from both sides of the equation. Okay, so you have 9 minus 7 is 2, and we have that 2 is equal to 2x, and we have with division by 2, okay, we're going to have an apparent solution with x at 1, and you can go back and check, okay, and without writing all the details. Okay, so we got in the equation, so we got 1 is equal to, and we have negative 2, and again for x at 1, 2 times 1 is 2 plus 7 is 9, and the square root of 9 is at 3, and negative 2 plus 3 is 1, and we have that 1 is equal to 1. Okay, so this value will check out. Okay, now for the next item, okay, we have for problem 104. Okay, and we have here, okay, another similar sort of display. Okay, this time, okay, we have, once again, we have a constant by itself on the left, okay, and that number we have with 6, and we have that 6 is equal to 9 plus the square root of 5 minus 3x, and so in looking at what we have for this equation, okay, so again we have just a single variable term in x, and that is going to be, okay, with the square root of 5 minus 3x. Okay, so looking at what we have in isolating the radical, okay, so I can take 9 away from both sides of the equation. Okay, so you have 6 minus 9 is negative 3. and we had that negative 3 is equal to the square root of 5 minus 3x. Okay. And this time around, notice before, okay, when we had it down to a constant on one side and the radical on the other, okay, I could follow through with 3 since this was a positive value. But in the case of what we have here, we got a situation trying to reduce a radical to negative 3, and this is a violation of the principal square root rule thanks to the constant being a negative. Okay, and so for what we have for number 104, we need not continue because there will be no solution. Again, that is because of the requirements laid out by the principal square root rule. All right, now for what we have in the group, okay, now we have this time transitioning over to the appearance of a different letter, okay, and this is going to show up twice. And in the case of number 105, okay, this time we're looking at the letter M, whereupon we have the square root of m plus 18, okay, followed by the addition of 2 is equal to m. Okay, so for this one, okay, as I have done before, okay, I can isolate the radical. In this case, this will be done by subtracting 2. Okay, so we have in the setup, so I have the square root of m plus 18 is equal to m minus 2. Alright, so I have the isolated radical term with the square root of m plus 18, and m plus 18 I can free up from the square root upon squaring both sides of the equation. Okay, so we have in the case of squaring, okay, so left hand side, okay, so this will become m plus 18. And for what we have to the right, okay, so I have a binomial to be squared. And again, this is going to be m minus 2 times itself. And again, we have, in following through, okay, so we have m squared, and again have back-to-back identical outside and inside products with negative 2m and negative 2m, and combining, okay, we have the trinomial, whereupon we have m squared minus 4m plus 4. Okay, and this will form the terms on the right hand side. Okay, so we have the establishment of a quadratic equation. And if I display what I have in standard form, okay, notice we have the highest order term is m squared, and this is situated on the right. And if I move the terms from the left hand side over, so I'm going to move the m as well as the 18. Okay, so if I subtract the m as well as the 18, right, so we'll have that 0 is equal to m squared, and negative 4m minus m becomes negative 5m, and 4 minus 18 is negative 14. Okay, and I can factor this trinomial and even factor on the right hand side. But what I'm going to do here, I'm just going to switch the order, kind of like going from b is equal to a to the logical equivalent display of a is equal to b. And so we have, with the factors in m, okay, so m squared will go to m and m. Factors of negative 14, whose sum or difference will be on the minus side at negative 5. This signals that more weight will be given to the subtraction than to the addition. And so upon looking at what we have and utilizing, okay, the zero product property, if I set m plus 2 equal to 0, I'm going to have that m is equal to -2. As for m minus 7, if I set this to 0, okay, we have an apparent solution with 7. Okay. Now, again, since I work with even root radicals, okay, it's those types of radical equations, okay, that checking is strongly recommended. So if I plug in -2 for m, okay, so -2 plus 18 is 16. Got plus 2 is equal to m, and square root of 16 is only +4. And for what I have here, 4 plus 2 is 6, and that's what I have on the left. But what I have on the right, okay, is -2. So -2 is not going to check out, and this will be what is regarded as an extraneous value. And extraneous values are those apparent solutions that fail to become official solutions once you check out. And okay, so the potential for there to be two solutions ceases to exist, and so we're looking to see if we have so much as one solution. And so testing out 7, with m at 7, 7 plus 18 is 25, and so we have the square root of 25, and we have plus 2 is equal to m, which we have again established at 7. Square root of 25 is 5. We've got 5 plus 2, 7 on the right, and 5 plus 2 is 7, and 7 is equal to 7. Okay, so that would check out, and so we have the solution for m to be at 7. All right, now in looking at what we have also where we had the variable to show up twice, and we have for number 106, okay, this time we're going from the letter m to the letter n, and for what I have here this time, the radical term is going to be the square root of 2n plus 29, and we have followed by the addition of 3 is equal to n. Okay. And again, looking at isolating this radical term, okay, so I can deduct 3 from both sides. So in the rewrite, I'm going to have the left hand side, okay, so I have the square root of 2n plus 29 is equal to n minus 3, and I can eliminate the presence of the radical again by squaring both sides. Okay, so the left hand side, okay, we're going to have it 2n plus 29 again for the square of n minus 3. Again, we'll have n minus 3 times itself, and we have in the expanding, okay, so we've got n squared, and we have back to back negative 3n terms for the outside and the inside products, and the last product is going to be 9. Okay, so this will come out to n squared minus 6n plus 9. Okay, so going back to our equation, okay, so we have a quadratic equation in the letter n, okay, and the highest degree term, okay, we have an n squared, again, which is situated to the right, and just looking at moving again the variable terms from the left hand side. So you have subtracting 2n as well as 29, and so we're going to have 0 is equal to n squared, and negative 6n and negative 2n will be minus 8n, and 9 minus 29 is negative 20. And again, I can just rearrange the terms. Again, you could factor on the right hand side. And so we have in utilizing the zero product property. Okay, so looking at n squared. Okay, so this will go to n times n. And factors of -20, that will add up to -8. Okay, so in this case, we will have more weight applied to the subtraction than to the addition. So we have n plus 2 and n minus 10. And setting each of the factors to 0. Again, we have an apparent solution at -2. And from n minus 10, we have the other possible solution at 10. And we have, just looking at examining what we have for these values. Okay, so if I check n is equal to -2. Okay, so I got 2 times -2 is -4 plus 29. So the square root of 25 plus 3 is equal to n, again, which we have assigned at -2. You notice in the follow through, square root of 25 is 5, and 5 plus 3 is 8, which I have on the left, and we have a mismatch here because 8 is not equal to -2. Okay, so we're back to where we have an extraneous value, and for checking out what we have for 10. So we have 2 times 10 is 20 plus 29 is going to form the square root of 49. And we have plus 3 is equal to 10, and the square root of 49 is 7. And we have 7 plus 3 is 10. So we got 10 to the left and also 10 to the right. So the value of 10 checks out. And so that is going to be the unique solution for this radical equation that we have in problem 106. All right. Now, I'm just shifting gears a bit. Okay, now we are continuing with radical equations. And for what we have in the case of 107, this time we're looking at a different root. And in this one, so we're going from square roots to cubic roots. And for 107, okay, now we have -4 times the cubic root of 2x minus 5. And now followed by the addition of 6, okay, is equal to 10. And just looking at for what we have in the setup, okay, so you have a single radical term, and I'm going to isolate, so I'm just going to move the 6 over. Okay, so in the rewrite, okay, with the radical term by itself, we have -4 times the cubic root of 2x minus 5 is going to be equal to 4. And here I can simplify and take care of the coefficient -4 upon dividing by -4. So to the left, -4's will cancel. So at this stage we have the cubic root of 2x minus 5 is equal to, and 4 over -4 is going to be -1. So I have a single radical term with the cubic root of 2x minus 5, and this is set equal to -1. Now if I had an even root radical, like a square root or a fourth root, and I'm trying to set it equal to a negative constant, I would have a violation of the principal square root rule, and there would be automatically no solution. However, the requirements that we have for cubic roots and other odd roots, those are immune from the restrictions concerning the principal square root rule. So I can have odd roots to reduce to constants that are negative. Okay, so I can continue. And we have upon eliminating the presence of the cubic root, we have by cubing both sides. So left hand side, okay, we have 2x minus 5, and to the right for -1 cubed, okay, this will be -1, and so we have a two-step linear equation, okay, and so we can isolate the 2x. And so adding 5 to both ends, okay, so we have 2x is equal to -1 plus 5, which is 4. And we have with division by 2, we have the x is equal to 2. Okay. And again, since I'm dealing with an odd root radical, okay, if the algebra is done correctly, okay, you're not going to have extraneous roots as you would in the case potentially of an even root radical equation. And now with odd roots, we have in the next item, and so we're going back, okay, to where we have another odd root expression, but this time not a cubic root but a fifth root. And for what we have in number 108, okay, we have -3 times the fifth root of 4x minus 1, followed by the addition of 2, okay, is equal to 8. And so for what I have here, again, I can isolate the radical term, and we have upon taking 2 away, so -3 times the fifth root of 4x minus 1 is equal to 6. And getting the fifth root of 4x minus 1 by itself, and this can be done by dividing by -3 on both sides. And the reason I'm going with division is that for the constant that will be on the right, that is going to be an integer. If I had a fraction that would not reduce, I'll probably keep both sides as they are. But for what I have in this pathway, okay, so I had the fifth root of 4x minus 1 is equal to, and 6 divided by -3 is -2. Again, so an odd root expression can reduce to a negative constant. And so I can continue the pathway to arriving at any solution for x. Okay, so to eliminate the radical, okay, I cubed to get rid of cubic roots, and now for fifth roots, I'm going to take the fifth order to which both sides will be raised. And so for the left hand side, fifth root of 4x minus 1 to the fifth, this will become 4x minus 1. To the right, you got -2 to the fifth. So you're going from like -2 to 4 to -8 to 16, and then times -2 once more. We have -2 to the fifth to land at -32. And so looking at isolating the variable term, and we have upon adding 1 to both sides, so we have 4x is equal to -32 plus 1, so we are going to have -31. And we have a division by 4. Okay, so we have a non-integer value with a negative fraction minus 31/4. Alright, and so again with odd roots, okay, the principal square root rule does not apply. Now, in looking at kind of going back, and again, for equations that have two radical terms. And again, those items can get to be rather tedious. And for what we have in the case of 110, okay, this time we're looking at a different letter. In D, okay, and here we have in the display we have two radical terms, and we have a difference of square root expressions. So we have the square root of d plus 4 minus the square root of 6 plus 2d is equal to negative 1. Right. And again, I can isolate either of the radical terms. I say probably just for kind of a clean display. Okay, I can get the square root of d plus 4 by itself. But I could also isolate the other one, but okay. So if I just move the square root of 6 plus 2d over, so we have the square root of d plus 4 is equal to negative 1 plus the square root of 6 plus 2d. Okay, and just as I had eliminated the presence of the square root for a single term by squaring, okay, and once again I'm going to square both sides, okay, but it will eliminate the radical on the left, but you're still going to have a remnant from squaring out what's going to be negative 1 plus the square root of 6 plus 2d. All right. Now for the easy part, relatively speaking, okay, so the square of the square root of d plus 4, okay, that is going to be d plus 4. Now, where we have in terms of squaring out the sum of these terms, okay, so if I FOIL out, I've got negative 1 times negative 1 is a positive 1. You've got a negative 1 times the square root of 6 plus 2d. Inside product, you got negative 1 and the square root of 6 plus 2d, so you have another negative square root of 6 plus 2d. And for the last product, you got identical square root terms. And anytime you have identical square root terms and they're multiplying each other, you're just going to have that term inside the radical and the radical to go out. Okay, so you have the first, outer, inner, and last products. And for what we have in the ensuing development, okay, so at the front I have a constant, and guess what? I can combine 1 at the front with the 6 from the last product. So 1 and 6 is 7. And if I combine the outside and the inside products, you got minus 1 square root of 6 plus 2d minus another 1 times the square root of 6 plus 2d. And for the last product, I've already joined 1 and 6, and so I have 2d left over. And so going back to our equation, if you notice, it took care of the square root containing d plus 4 after squaring both sides, but I still have remnants of the square root of 6 plus 2d. And I'll soon take care of that. Okay, so just as I had isolated the square root of d plus 4. I'm going to isolate this radical term. Okay, so I have this to the right, and I'll just move the 2d as well as the 7. So looking at what we have now, d minus 2d is negative d. 4 minus 7 is negative 3. Now, I can technically go ahead and square both sides. Let's say that, if you notice, all these terms have leading coefficients that are negative. So I can just kind of clean up here. So I can just multiply or divide the equation by negative 1. In other words, make all these negatives into positives. So we have d plus 3 is equal to 2 times, okay, the square root of 6 plus 2d. Alright, and so for what I have here, okay, now I can technically divide by 2, but I'll be looking at fractional coefficients. And if you want to stick with just the whole numbers or the integers, I can just go ahead and square both sides. We have, upon doing so, alright, so we have d plus 3 quantity squared, and squaring this binomial. Okay, so we have a squared trinomial. Whereupon we're going to have d squared plus 6d plus 9. For what I have to the right now, we got 2 squared is 4. Square root of 6 plus 2d is going to be 6 plus 2d. Again, to the right, I have squared the factors, but the squaring does not already take care of the multiplication in advance. Okay, so I got d squared plus 6d plus 9, and we have with distributing. Okay, so I have 4 over the quantity of 6 plus 2d. Okay, so that's going to be 24 plus 8d. And now I have a quadratic equation and if I write this in standard form, now we have the highest degree term is d squared, which is to the left. Now I'll just move the terms from the right over. And so I have in the rewrite, so we have d squared, 6d minus 8d is negative 2d. 9 minus 24 is going to be negative 15. And here we have d squared minus 2d minus 15. And we have with factoring, okay, so factors of negative 15 whose sum or difference will be at negative 2. Okay, again, this will signal that more weight applies to the subtraction than to the addition. And we have with the zero product property. Okay, so if I have d plus 3 equal to 0, I'm going to have that d is equal to negative 3. For d minus 5 equals 0, I'm going to have that d is equal to 5. Okay, so you have two apparent solutions. indeed this is a rather long equation. Okay, now if we check what we have with these apparent solutions, so this is the equation we started out with. Right, so plugging in -3. -3 plus 4 is 1. And 6 plus 2 times -3. Okay, that is going to be 0. 6 minus 6 is 0. Square root of 1 is 1. 1 minus 0 is 1. However, the right hand side of the equation is -1. And so we have -3 is going to be extraneous. Now for what we have for D is equal to 5. Okay, so with D at 5, square root of 5 plus 4 is going to be the square root of 9. 2 times 5 is 10. 6 plus 10 is going to be 16. Okay, square root of 9 is 3. Bring down the subtraction. Square root of 16 is 4. And 3 minus 4 is -1. And -1 is equal to -1. So 5 is going to check out. Okay, and so for this difference of radicals equation, okay, we have one solution, and this is going to come out to 5. Okay, and I'll say that out of the bunch. This is going to be, I would say, by far the most challenging problem, not only because there are so many operations, but also because you have so many details to look into. A lot of squaring involved and examination, since we were working with even root radical terms. All right, and just kind of going back, okay, to radicals again, but in the form of where we have correspondence with non-integer exponents. Again, going back to the rule here. So if you have a non-integer exponent or anything in the form of a to the m over n, again, you have translating in terms of radicals. Okay, the denominator of the exponent is going to dictate, okay, just what the index number of the radical is going to be. So a to the m over n is going to be the nth root of a to the m. Now, for what we have in the case of equations consisting of non-integer exponents, let's say we have 2 times the quantity of x plus 5 raised to the 2/3 is equal to 18. Okay, and I can do here, okay, so gosh, like your base a is represented by x plus 5, m over n, we have 2/3. And what I can do here is I can isolate x plus 5 to the 2/3. If I just go ahead and divide the equation by 2. Okay, so I have here x plus 5 to the 2/3 is equal to 18 halves, okay, which is going to be 9. Okay, so making the transition, okay, from a to the m over n and writing as a radical. Okay, all right, so we have the type of root is going to be cubic. So I'm looking at the cubic root of x plus 5 to the 2nd is equal to 9. Okay, so again, I'm just kind of using this particular property. Okay, so rewriting in terms of a radical. Okay, so I have the cubic root of the square of x plus 5 is equal to 9. And I want to solve for x. So I can start out getting rid of the cubic root upon taking both sides and raising to the third degree. Right. So on the left, okay, the radical goes out, and that which was contained is freed up, so I now have the square of x plus 5. Now for 9 to the third, 9 times itself is 81, and in turn, 81 times 9 is going to be 729. So here I have the square of x plus 5, okay, is equal to 729. And then crossing over to the stage here, I can apply the square root property of equality. Okay, again, so if I have x squared equal to p, I have x is equal to plus or minus the square root of p. And with x represented by x plus 5 and p by 729, I can say that x plus 5 is equal to plus or minus the square root of 729. Okay, and we have with 729, okay, this exists as both a perfect cube and also a perfect square. Again, like the cubic root of 729 is 9. Now the square root is going to be a substantially larger number with 27. And so we have, and finding out the values of x. So when it's going to come forth, okay, from setting x plus 5 equal to negative 27 on the lower end, we have also on the upper end we have x plus 5 is equal to 27. And for what we have in these equations, okay, so we take 5 away from both sides. Okay, so if x plus 5 is equal to negative 27, and negative 27 minus 5 is negative 32. And for x plus 5 equal to 27, okay, we're going to have the x is equal to 22. Okay, so we have a pair of solutions here. And again, the nature of the radical was a cubic root, so there's nothing like the principal square root rule to deal with. And for what we have in the next item, okay, so you still have the same exponent. And it's in number 114. Okay, so this time we have 3 times, okay, the quantity of x minus 6 to the 2/3, okay, is equal to 48. And if I divide the equation by 3, okay, so left hand side is going to be x minus 6 quantity to the 2/3, and we have 48/3, okay, becomes 16. Okay, and just translating again to a radical. So again, we have the denominator 3, signaling that we have a cubic root. And this time we have the cubic root of x minus 6 to the 2nd, and we have is equal to 16. And just when you think that 729 is large, okay, well, guess what? 729 came from cubing out 9, and now we're about to cube out the number 16. Okay, so we have here, again, eliminating the radical. Okay, so left hand side, we'll have the square of x minus 6 And to the right, we have 16 times 16. You already have a 3-digit product with 256, and then multiplying by 16 once more. And this time will come out to 4,096. And here, like 729, 4,096 is both a perfect cube and a perfect square. And if I apply the square root property of equality treatment to problem 114, okay, we're going to have the square of x minus 6 lowered to just x minus 6. And to the right, I'm going to have plus or minus the square root of 4,096. And 4,096 is going to have a square root value at 64. Okay, and so we have for x, we have two values to apply. And one's going to be where we have it such that x minus 6 is equal to negative 64. And also where we have x minus 6 is equal to positive 64. So we have with x minus 6 equal to negative 64. Okay, so if I add 6, we'll have that x is equal to negative 58. And for x minus 6 equal to 64. Okay, so if I add 6, okay, in this case we'll have the upper value is going to be at 70. Okay, so there'll be two solutions here for x with the numbers negative 58 and 70. Right. So both of these problems had the power to which the basis was raised to be at 2/3. Okay, but now let's say that if I change things up and we have for number 115, and we got, this time we have the exponential base. Okay, we have the quantity of 3x plus 1, and this time we have raised to the 3/2 power, and we have plus 2 is equal to 66. Okay, and for this one, okay, I can start out and isolate the variable expression. Okay, so I'm going to take 2 away from both sides. So what I have here, I'm going to have the quantity of 3x plus 1 to the 3/2 is equal to 64. And now I can rewrite what I have as a radical. Okay, so now again the denominator value is 2. Okay, so that's going to be second root, which will be a square root, and I have 3x plus 1 raised to the 3rd is equal to 64. Okay, so again, got a second root, so this will be a square root. Okay, and in the square root of an expression, we have set equal to 64. 64 is a non-negative value, and so I can continue. Okay, and so no, there's no violation of the principal square root rule. So I can continue by eliminating the radical, so I can square both sides. So for what I'll have here, so by squaring, okay, the radical is taken care of. And so left hand side, okay, I have the cube of 3x plus 1, and for 64 squared, we just dealt with the square of 64 when we had cubed out 16. Okay, so you got 4096. once again. And now, so we got 3x plus 1 quantity cubed is equal to 4,096. Okay, I'm just going to write this again. Now, if you notice, okay, in the previous steps, okay, I used a radical, got rid of it by applying exponents. Now, I'm going to go in the other direction. I'm going to get rid of this cube by taking the matching radical. In this case, will be by taking the cubic root of both sides. Yeah, so we're doing quite a few shifting of gears. In fact, just shifting to the point of going in reverse. Okay, so we have here the cubic root of the cube of 3x plus 1. This will be 3x plus 1. And the cubic root of 4,096. Okay, so that will be at 16. And we have, for the two-step linear equation, again, I can isolate the x term. Okay, so subtracting 1. Okay, so I have 3x is equal to 15. Then we have a division by 3. This will come out to 5. Okay, so 5 is going to be the solution that we have in this problem. Okay. Now, for what we have in the case of 116, okay. Okay, so got 2x minus 1 to the 3 halves minus 3 is equal to 122. Okay, so we have our variable expression, okay, to be an exponential base, again, taken to the 3 halves power. Again, if I isolate, so I have 2x minus 1 to the 3 halves is equal to 125. And again, just going from non-integer exponent to its radical equivalent, just like what I did earlier. Again, the 2 in the denominator signals that we have a square root. This time this will be the quantity of 2x minus 1 to the 3rd. So here, okay, so I got a square root. Again, I can eliminate the square root by squaring both sides. Okay, so for what I have to the left, okay, so this will be the cube of 2x minus 1, and 125 squared is going to be a very large number in comparison to what we've worked with. So we have 15,625. Okay, so the radical is eliminated, but I still have that remaining cube applied to 2x minus 1. Okay, still remaining. Okay, so I can take care of the presence here by taking the cubic root of both sides. Okay. So to the left, okay, so I have 2x minus 1. And for the cubic root of 15,625, okay, so this will be at 25. Now I just mentioned earlier, when we translated to square root. Again, you had the square root of an expression equal to a positive 125. Again, no negative, constant. So again, I still had the green light to proceed. Okay, so we got with 2x minus 1 equal to 25. And we have isolating the 2x by adding 1, so I have 2x is equal to 26. And we have a division by 2. It will come out to x is equal to 13. All right. So quite a bit of work entailed, okay, with the radical equations, especially if you got two radical terms, and also if you have non-integer exponents. Now, just to kind of give you a segue to the remaining item from the set, and just a little while back, okay, we had looked at reducing radicals, like in the case of just having non-integer solutions, and also if you had like square root terms, like after utilizing the quadratic formula to solve an equation, and kind of going back to what we had for perfect squares. And also in the mix you have perfect cubes. Now for the natural number of perfect squares, or the positive perfect squares, again you have like 1 squared is 1, 2 squared is 4, 3 squared is 9, and continuing with square of 4, square of 5, as well as that of 6, 7, all the way up to 10 squared. Okay, so this is what you have among the first 10 natural number perfect squares. Now for the perfect cubes, okay, like 1 cubed, this can be 1, and 2 cubed would be like 4 times another 2, which is going to be 8. 3 cubed would be like 9 times 3, which is 27. 4 cubed, 4 times 4 times 4, or 16 times 4, have it 64. And 5 cubed, we have 25 times 5. 6 cubed would be 36 times 6, which is 216. 7 cubed would be like 49 times 7, which is 343. And the cube of 8, or 64 times 8, is 512. And again, the number we dealt with earlier, 9 cubed, or 81 times 9, we have 729, and 10 cubed, or 100 times 10, so we have 1000. Okay. Now, for what we have in the case of 117, we're working with a different letter again. We're back to m, and we have m to the 3/4 is equal to 5. Okay. All right, so I have m to the 3/4, and we have with the translation to a radical. So you have the denominator is at 4, and so we have the 4th root of m to the 3rd, translating what we have in radical terms. So you got an even root expression set equal to a non-negative constant. Okay, so I can proceed. And what I can do here is that I can take care of the 4th root by taking both sides and raising to the matching power or degree, which is going to be 4. Okay, so the left hand side, okay, this will become m to the 3rd. Okay, after we clear away the excess of the exponent and the 4th root. Now for 5 to the 4th, okay, this will become 625. Again, 5 times 5 is 25, times 5 is 125, and then times 5 is 625. So now I have m to the 3rd is equal to 625. And again, I'm looking at solving for m and I can undo the presence of the cube of m, this time by applying the matching radical, in this case, which is going to be the cubic root. Okay, now the cubic root of m to the third, okay, this will go to m. Okay, now for what we have in the case of the cubic root of 625, okay, now technically, okay, 625 would be a perfect square, but it is not among the perfect cubes that you have. And if I were to look at reducing, say if I had to give an exact value for m in reduced terms, okay, so we have with 625, okay, you notice 625 is between 512 and 729, but it is not among the perfect cubes. And so if I look for the highest perfect cube divisible into it, well, 512 is not it, nor is 343 or 216, but we do have 125. As the highest perfect cube divisible into 625, and 125 into 625 is going to be 5. And just looking at splitting up, so we have the cubic root of 125 times the cubic root of 5, and cubic root of 125, this will go to 5, and I cannot reduce the cubic root of 5. Okay, and so it's going to turn out that with this reduction, this will turn out to be the solution of what we have for m in reduced radical terms. Okay, so for m, this will end up as being 5 times the cubic root of 5. All right, now there's quite a bit of work here with the radical equations, and again, the other day we had absolute value equations, and just for the items, okay, that we have in the set, okay, so we have that k is non-negative, and we have that the absolute value of x is equal to k, then we have the x is equal to plus or minus k. Again, you have your possible values to result for x, where we have with negative and positive k. And for what we have in the same section, now we have with number 90. Okay, so we have in this setup, now we have an absolute value equation. Now we've got 4 times the absolute value of 2t plus 7 plus 2 is equal to 22. And again, we got the absolute value of 2t plus 7. And again, do not treat 4 times the absolute value of 2t plus 7 as you would 4 times the binomial 2t plus 7. So the absolute value bars and the parentheses, they're not to be treated as the same. Okay, so what I can do here is I can isolate the absolute value of 2t plus 7. So working around what I have here, okay, so I can subtract 2 from both sides. Okay, 22 minus 2 is 20. All right, so I have 4 times the absolute value of 2t plus 7 is equal to 20. And getting the absolute value of 2t plus 7 by itself. I can just undo the multiplication by 4 upon dividing both sides by 4. Okay. So we have in this layout, okay, so we have on the left, we have the absolute value of 2t plus 7 is equal to 5. Okay. So we have at this point, have the absolute value of x to be the absolute value of 2t plus 7, and k is equal to 5. So just leading up to the development of the opposite sign values of k, once I remove the absolute value bars, we'll have a system of equations where we're going to have 2t plus 7 is equal to plus or minus 5. And setting things up, okay, for solving for t. Okay, so we have with our equations, okay, so we have at the lower end, okay, we have 2t plus 7 is equal to negative 5. The upper end, I have 2t plus 7 is equal to 5. Here we have negative 5 minus 7 is negative 12. And if 2t is equal to negative 12, we'll have that t is equal to negative 6. And for 2t plus 7 is equal to 5, if I take 7 away, we'll have that 2t is equal to negative 1. T is going to be equal to negative 1, but for 5 minus 7, that is negative 2. And if I divide by 2, we have that t equals minus 1. So we have two negative values for t in this instance. And so we have minus 6 and minus 1. Right. Now, for what we have in the case of the next absolute value equation, okay, and we have with number 91, okay, this one potentially a little bit tricky, and we're looking at solving in terms of the variable c, and right now we got negative 3 is equal to the negative of the absolute value of c minus 7 plus 1, and if I isolate the absolute value of c minus 7, so what I can do is I can move at least the 1 over. Okay, so if I apply subtraction, and here we have negative 3 minus 1. Okay, so I have negative 4. And we have negative 4 is equal to the negative of the absolute value of c minus 7. And for what I have next, I can either multiply or divide the equation by negative 1. So we got that 4, positive 4 is equal to the positive absolute value of c minus 7. And what I can do here, kind of just reordering, kind of going from b is equal to a is equal to b format, where I have the absolute value of c minus 7 to the left and 4 situated to the right. So here we got the absolute value of x represented by the absolute value of c minus 7, and the k is going to be 4, and once I remove the absolute value bars, we have c minus 7 will be equal to those numbers 4 units away from 0, and those numbers being positive and negative 4. So for the possible values of c that we have, will come from setting c minus 7 equal to negative 4, as well as c minus 7 equal to 4. Okay, so upon adding 7 throughout both sides of the equation, so if c minus 7 is equal to negative 4, c is negative 4 plus 7, which will be positive 3. And if c minus 7 is equal to 4, c is going to be 4 plus 7, which will be 11. Okay. Right. Now, in the case of what we have with absolute value equations, okay, and these will kind of come to quick conclusions. Yeah, just for number 93. Okay, so we got in the variable y. Okay, so we got 2 is equal to 8 plus the absolute value of 11y plus 4. Okay. And this one. Okay, so if I isolate the absolute value term and just take 8 away from both sides, so we got 2 minus 8 is negative 6. Okay, and if I just reorder or switch the order, so I'm trying to say that the absolute value of 11y plus 4 is equal to negative 6. But again, if you notice, we have negative 6, and the absolute value of an expression cannot reduce to a negative constant. So the absolute value of an expression cannot be negative. So in the case of 93, okay, we have no solution. And for the case in number 94, okay, so we have 6 is equal to 7 plus the absolute value of 9z minus 3. And so if I isolate the absolute value of 9z minus 3, so if I take 7 away from both ends, okay, so I have 6 minus 7 is negative 1. And saying negative 1 is equal to the absolute value of 9z minus 3. Again, if I just switch the order, okay, and again, trying to say that the absolute value of an expression is equal to a negative. Again, I have that same roadblock once again. So like number 93, okay, number 94 results in no solution. All right, now for what we have among the remaining absolute value items. Okay, now 96, okay, this is a little bit of a trick one. Where you have absolute value terms set equal to each other. Okay, so here we have the absolute value of 2a minus 3 is equal to the absolute value of a plus 2. Okay, and just kind of give you a little bit of a segue. Okay, see if I had like the absolute value of x equal to 7, you have x is equal to plus or minus 7. Okay, so you have just like absolute value of plus or minus 7 is equal to 7. Now we have with say with 2a minus 3 as well as a plus 2. Okay, so if I have like x is equal to, or I'll tell you what, I'll do it this way. If I have that absolute value of x is equal to 2a minus 3, guess what? X would be equal to plus or minus what I have for 2a minus 3. And likewise, if I had the absolute value of x equal to a plus 2, x be equal to a plus 2 as well as its negative. Okay, so just taking what we have here. So two quantities with an absolute value of 2a plus 3. So you're looking at plus or minus 2a minus 3. And for a plus 2, yeah, plus or minus a plus 2. All right, and so just taking what we have now, what you need, okay, is that you just need, for these, you don't have to consider all four combinations. You just need one pairing where you have the same sign and also opposite sign. So one route is I can just kind of map together, let's say a positive 2a minus 3 with a positive a plus 2, where you had the same sign, and also for opposite sign, let's just say I can have map, let's say the positive of 2a minus 3 with the negative of a plus 2. If I go with like negative, positive, negative, negative from 2a minus 3 to a plus 2, I'm going to have a duplication of the pairing I'm choosing. So if I go with, let's say, the positive of 2a minus 3 is equal to positive a plus 2, again, removing parentheses, there will be no sign change. Okay, so I'm down to 2a minus 3 is equal to a plus 2 and looking at solving for a, it's about 2a, if I take away a, we have a minus 3 is equal to 2, and if a minus 3 is equal to 2, we have that a is equal to 5. And say we have with, you got the possible pairing, say the positive of 2a minus 3 is equal to the negative of a plus 2. Okay, so left hand side, no sign change. No sign. And for what I have to the right, the opposite sign of a plus 2, this will be negative a minus 2. And if I combine variable terms together, okay, so the left hand side, and we'll have 3a minus 3 is equal to negative 2. And we have upon following through. Okay, so if I add 3 to both sides here, okay, so we have that 3a is equal to positive 1, and we have with division by 3, okay, we have that a is equal to 1/3. Okay, so for what we have in the case of 96, yeah, that one quite different. Okay, so one value of a is going to be at 5, and we have the other one is going to be a non-integer. We're going to have the fraction 1/3. All right, now so far we have dealt with real numbers. Okay, and for what we have for the entry into the next section, and this is going to be with what we have with the complex number system. Okay, for the complex number system, okay, I was going to give you some of the tidbits we have regarding complex numbers. Now, the foundation of a complex number, some books might have it as the letter J, but most I have seen have the letter I, and I is equal to the square root of -1, and the square of I is going to be at -1. And let's say that for the complex number system, if I were to reduce in terms of I, let's say we have, first of all, okay, say if I have something like the square root of -25, guess what? Okay, so we've got a perfect square number with 25, and say if I were to factor out, say I have the square root of 25 times the square root of -1. Square root of 25 is 5, and guess what? I is going to be the square root of -1. So for this reduction, that's going to end up at 5i. And let's say that if I have something that's not quite a perfect square number, say if I have, say, the square root of -20. If I were to reduce, okay, so I can factor out the -1. Now for the number 20, 20 is not a perfect square number, and the highest perfect square divisible into it is going to be 4. Okay, and for what I have here, okay, so for the square root of 4, square root of 4 is 2, and 5, okay, not a perfect square, and the highest perfect square divisible into it is only 1, so that square root of 5 remains. And so for the square root of -20, we have 2 times the square root of 5 times I, and some might also write this with the letter I in front of the radical. And for what we have, like in the case of what we have for the letter I, I'm going to kind of do a little shifting of the order here. Now let's say if we have so I have equations with complex roots. Okay, so you have for equations that have complex roots. Okay, we're going to have here, let's say if I'm looking at solving for x. And let's say that, now we've dealt with stuff like differences of squares and solve by factoring. Let's say if I have a sum of squares. Okay, so if I have like x squared plus 4 is equal to 0. Okay, now I cannot factor into real integer coefficients the sum of squares with x squared plus 4. I can't do it as I could with the difference of squares. So for what I have here is that for x squared plus 4 is equal to 0, if I separate x squared from the 4 by subtracting, so we have x squared is equal to negative 4, and just kind of taking the square root property of equality. Okay, so going from x squared is equal to p to x is equal to plus or minus, okay, the square root of p. Guess what? We have x equal to plus or minus the square root of negative 4. Now the square root of 4 is 2. Now the square root of negative 4 is going to be not just 2, but 2i. So we come out to negative 2i as well as 2i. I'll give you like another case here. If I've got, let's say, kind of touching upon the quadratic formula, and let's say if I have like x squared plus 3x plus 7 is equal to 0. Okay. Okay, so I have x squared plus 3x plus 7 is equal to 0. Now from what we'll have here, so I cannot factor this trinomial, but I can use the quadratic formula. So for what we have here, okay, so you got A at 1, B at 3, and C at 7. And if I fill in, so for negative B, okay, so I have negative 3. We have plus or minus. Okay, we got the square root. Now b squared is 3 squared. We got minus 4 times a, which is going to be negative 4 times 1 times c, where we have multiplication by 7. And we have all over 2 times 1. So the only thing I've done is to substitute. Okay, so about 3 squared is 9. Negative 4 times 1 is negative 4. Negative 4 times 7 is negative 28. And we have all over 2. And we're getting closer to the roots here. So we got negative 3 plus or minus. Okay, if you notice we have 9 minus 28 is going to be a negative 19. Now 19 is a prime number. And so we have square root of negative 19 is going to be the square root of 19i. And just for what we have in compact form, okay, you have negative 3 plus or minus the square root of 19i over 2. And there's the thing that's referred to as standard form. And if I were to separate okay, say in standard form. Now, just mention this. Okay, just separating the leading term apart from the I term. Okay, so we had the standard form of a complex number. Is a plus bi. Okay. And again, we have at the root, again, you have I is equal to the square root of negative 1 you have I squared is equal to negative 1, and say with these last examples here, okay, say if I write in terms of a plus bi. Let's say I have for case number 1, let's say if I have something like the if I have like 3 plus 2 plus the square root of negative 49. Okay, so got 3 plus 2. Those are real values. And just cluster those together. And for the square root of negative 49, square root of 49 is 7. But for the square root of negative 49, okay, that is going to be 7i. Okay, so this one, okay, kind of a short answer item. But let's say that if I have, say in case of variables, let's say if I have like a couple of complex numbers, let's say if I have 2 plus the square root of negative 16 plus 3 minus the square root of negative 81. Okay, and what I can do here is that with the radicals, I can just write in terms of the letter I. Now the square root of negative 16 is going to be 4i. And we have square root of negative 81, that's going to be 9i. So I'm looking at subtracting 9i. And once I take out the parentheses, okay, so we got 2 plus 4i plus 3 minus 9i, and combining, so you had 2 plus 3 is 5, and we got like terms with 4i and negative 9i. So here we're going to have 5 minus 5i. Now when it's just direct addition and subtraction, it doesn't require a lot of detail in terms of getting to the standard form. But let's say that if you're looking at multiplying complex numbers, so you have 3 plus 2i, and we'll say we have times the quantity of 4 minus 5i. Okay, so we got quantity of 3 plus 2i times that of 4 minus 5i. And if I take the FOIL approach, okay, so we got 3 times 4 is 12. Outside product 3 times negative 5i. That is negative 15i. Inside product we have 2i times 4. So we have 8i. Now for the last product, this is the one that you got to be careful with. You got negative 10i squared. And what I want to do here, notice the standard form we have a plus bi, so there is no I squared term that is involved. And let me just restate again, I is equal to the square root of negative 1, and we have the I squared is equal to negative 1. Okay, so for what I have at this stage, okay, so we got 12, now we got negative 15i plus 8i, so we have negative 7i. And in terms of what to do with the negative 10i squared, guess what? We got I squared is equal to negative 1 so negative 10 times I squared, that's going to translate to negative 10 times negative 1 and so we have with the proceeding, we have 12 minus 7i, and we have negative 10 times negative 1, that's going to be a positive 10. And we have for this result, 12 plus 10 comes out to 22. Okay, so we got a statement of subtraction. So like for a plus bi, your b can be negative. And so we have in this form we have come out to 22 minus 7i. Okay, so again, you have complex numbers, so it'll be those numbers that involve square roots of negative values.